Okay, welcome back. So our next speaker is Nicolle Gonzalez, who will tell us about a Skein Theoretic Carlsson-Mellit algebra.
Hi, everyone. Thank you for coming. I know it's probably early for some of you. So as Josh just said, I'll be telling you about some Skein Theoretic version of the AQT algebra or the Carlsson-Mellit algebra and its polynomial representation. So the plan is I'm going to eraser mode. The plan is I'm going to tell you a little bit about the algebraic story, the original algebraic story that is due to Carlsson and Mellit. And then obviously that means I have to tell you what this algebra is and what its polynomial representation is. Right, we're going to call that Vn. And then I'll pass over to a topological story where I'll tell you this is about basically I'll construct some sort of topological action here and topological operators. And then hopefully if I write quickly enough, I can tell you how to pass all of this to a categorical action. So we can construct the polynomial representation or realize it categorically. So I want to say that both of these things here are joint with Matt Hogancamp, and that's hopefully the core of what I'll tell you about today. Cool. All right. So with that in hand, I want to give you a little bit of motivation slash history about where this problem kind of initiated or where it fits into things. Right. So the main motivation, or I guess the origin story, comes from what's known as the shuffle theorem or the shuffle conjecture, which as a statement, it just says that, this is really fat. As a statement, it just says that the Frobenius character, yeah, I did spell that correctly, of the space of diagonal harmonics, which we're going to, which is given by delta En, where delta is this nabla operator, and En is just the elementary symmetric function. And then this is just saying that it can be expressed as a sum over a certain family of symmetric functions known as word parking functions. Now, a priori, all right, this is a theorem. Now it's been proven. And the point, though, is that in the proof of this theorem, which incidentally has a lot of, it just shows up all over in algebraic combinatorics, the Carlsson and Mellit constructed this algebra known as the AQT algebra. They introduced this AQT algebra and its polynomial representation, right, Vn. So this was introduced by Carlsson and Mellit in 2015. Right, and the reason it's, well, some of the reasons why it's interesting is, first of all, it's generated by multiple or two copies of the affine-Hecke algebra in conjunction with some raising and lowering operators. It contains copies of Daha's inside. It obviously played a crucial role in the proof of the shuffle conjecture itself, obviously, right? And then in the proof of the rational shuffle conjecture, which was due to Mellit in 2016. Right, this is Carlsson and Mellit in 2015. Which out of that, basically one of the things he showed is that you can realize the generators of the elliptic Hall algebra inside AQT, right? In addition, this representation was actually also realized geometrically in the work of Gorski and then Carlsson and Mellit on parabolic flag Hilbert schemes. So based on, if nothing else, just these three things, it seems like it's an interesting algebra to study. And if you drank the categorification juice a long time ago, like I did, you look at this and you're like, hey, let's categorify it. Why not? So this is kind of the motivation of where this algebra fits into things. So what is it actually? So in order to define it, we actually are going to define two separate algebras. The first one is what we're going to call the A algebra, right, which is sometimes known as just AQ. And we're going to define it in the following way. So it's the QTQ category. And it has some objects, right, which are just given by integers, positive integers. And then its morphisms are going to be generated by T1 through Tn minus 1, right? These are going to be seen as maps from n to n. Then we have d plus and d minus, which are going to be maps from n to plus or minus 1, depending if it's plus or minus. Then we have this other operator, we're going to call it phi, which is going to be defined in the following way. So it's a commutator between d minus and d plus, but it's weighted by some constants here in front, or some scalars, whatever, some parameters, let me say that. So d minus, d plus. All right, so we have these three things, and they satisfy certain relations. Namely, they satisfy the Hecke algebra relations for the TIs, right? And these are just telling you basically, well, the usual Hecke algebra relation plus the braid relations, right? Which I'm not going to write down because I'm hoping everybody can either look them up or knows them. Then we have the commutation relations, which I will give you. So that's just telling you that d minus and ti commute, and that d plus and ti almost commute, but not quite. And then we have these braid absorption relations, which tell you how the d pluses interact with ti's, right? So this is tq inverse of d plus. Then we have phi of d plus is d plus phi. These are viewed as endomorphisms from n to n plus 1, or maps from n to n plus 1. And then we also have how d minus interacts with things. So this is tq inverse of d minus squared, and then d minus phi is phi d minus tn minus 1. And here, these two are viewed as maps from n to n minus 1, right? So here's your algebra. A algebra has objects, just integers, and then it has a bunch of maps between the integers, which satisfy some crazy family of relations. All right. In addition, related to this, so if you're familiar with this algebra, you've seen it before, you've probably seen this in a different iteration where it probably has yi's, certain yi's as generators. So you can actually just take these as the generators and from them define what yi is. So let me just tell you that there's a very nice additional morphism that we're going to call yi, which is just defined in terms of these previous generators, right? So it's just Tn minus 1 inverse all the way to Ti inverse. And this is just a map from n to n. Okay, and what's interesting about this yi is that actually the Ti's and the yj's satisfy the relations of an affine Hecke algebra. Right, and in addition, they also behave interestingly with the other operators in the sense that they satisfy interesting commutation relations as well. So T, this is probably an N. This is probably an N, sorry, there's a typo somewhere. Yi, Ti, inverse, T1, D plus, and it commutes with D minus. Okay, whatever. So you have all these generators, all these commutators. You have this special thing, this special morphism. Let's call it yi. And then, in addition to this algebra, we actually also need to define a different algebra, a very related one, called A star. So the A star algebra, which is sometimes known as AQ inverse, right? And this algebra is, again, it's just the Q TQ category with the same objects. So the objects are just and in z bigger than or equal to 0. And then the morphisms here are given by ti inverse d plus star, d minus phi star. And then the relations are actually the same as with A, but with Q and T exchanged for Q inverse and T inverse, right? And obviously Ti swap with Ti inverse, D plus star with D plus, D minus stays the same, and Phi star with Phi, right? So based on this, you can probably guess that A is isomorphic to A star, right? Through this antilinear automorphism, precisely swapping the Ti, the starred operators with the non-starred operators, and Q and T with Q and T inverse, right? Great. So what is, any questions? Sorry, I'm going quickly because I'm concerned about time, but we're good? Great. Okay. Yeah, Ben, if I don't see the chat, so if I have a question in the chat or something, can you just interrupt me? Thank you.
You can ignore the chat. We'll.
Oh, okay. Okay, great. Awesome. In that case, what is the actual AQT algebra? So we're going to call it the Carlsson, two S's, Mellit algebra, right? Also known as the AQT algebra, is what? Well, it's the Q, TQ category again, with what? With the objects, no surprise, given by integers, right? And then the generators are going to be exactly, or sorry, the morphisms, generating morphisms are going to be exactly the same as for A and A star, meaning you have a D, D plus star, D minus, YI star, the same things, Phi star. But then the relations are, again, the same as for A and A star. So at this point, we've done nothing except basically glue the two things together. But then you have some compatibility that has to hold between A and A star, right? And these additional relations are these intertwining relations between the starred and the non-starred operators, right? Which are just basically telling you how these things have to interact. All right, so a priori, this algebra right now just seems like it's a bunch of mumbo jumbo. So let's maybe, once we get to this, talk about what the actual representation is. Y1 D plus star. Okay, cool. So here's the algebra. You take these two algebras with a bunch of operators and a bunch of relations, glue it together and add more relations. And great, you end up with this algebraic mess. So now we construct a representation for it. Questions? No, okay, awesome. So what is the polynomial representation, Vn? Let's talk about that. It turns out that this AQT algebra acts on this space Vn, this vector space, which we're going to define to be just basically the ring of symmetric functions with a bunch of y's, with n y's added to it. So x1, x2, right? So it's just really the ring of symmetric functions over QTQ with a bunch of extra variables, y1 through yn. And questions? No, okay. And what is the action? Well, the action of Ti of f is going to be given in the following way. So here, if you're familiar with the original work by Carlsson and Mellit, the normalizations are a little bit weird because we have different parameters, but they're equivalent. There's a map that you can construct. So just if it looks weird, trust me, it works. So here, we're going to let this be TQF minus, so TQ inverse YI minus T inverse Q, YI plus 1, del I of F, right? Here, this del I is really just the usual de Measure operator or the divided difference operator. And that what this is telling you is the TIs are just acting by de Measure Lustig operators. So these are just de Measure Lustig operators, right? And then you have the action of D minus of F, which is just going to be by T inverse Q to the residue of Yn. So sorry, I'm just giving you the full formulas. Just partly to show you how messy they are and how wonderful they become when you suddenly can just draw pictures for them. So this, I'll explain in a second what I'm writing. So this is some crazy plethistic notation, this right here. This is just a plethism that's sending basically pk, the kth power sum symmetric function, to itself plus tq inverse minus t inverse q minus y to the k. Right, oh, this should be yn, sorry, yn to the k. Right, and then you do some plethism.
Also tq power k, tq
right?
inverse power. Also tq inverse power k and t.
Oh yeah, sorry, this should be a k, of course.
And then what's that symbol? I can't, you're in the inside the plethism between
Epsilon?
the epsilon. Okay.
It's an epsilon, yeah. So the epsilon, it's because you want to differentiate between like negative signs and whether the variable carries a negative sign with it. So it's just plethistic notation that I don't want to particularly get into right now.
No problem.
The point is, it's some plethism. It doesn't really matter for what I'm going to do. I'm just giving you the full formula so that you understand. It's this like complicated procedure, right? So you take this plethism, you multiply by e, or by the elementary symmetric function, you sum all these terms up. You take a residue at yn. Anyway, so it's this complicated operator, and then you have d plus of f, which is defined again as tq inverse to the n. So you have all these operators, -1, Tn inverse f of, okay, x minus tq inverse minus t inverse q, yn plus 1. Right, again, some sort of plethistic operation. Then you can define d plus of f to be an analogous kind of construction, or d plus star, which is again just some sort of plethism. Right, and then this gamma is this automorphism from Vn to Vn, which is basically just defined by the fact that it sends 1 to 1 and it bumps your i's up every time, or your yi's. So when it acts on yi, it just goes by it, but it gives you a yi plus 1. And then, no, come back. What did I do? There it is. And then gamma of yn is just going to give you then q squared y1 composed with gamma. So it's just some particular endomorphism of Vn. And then lastly, you have the action of yi of f, which is just given by multiplication by yi on your function. All right, so the representation, you see it, it's kind of a mess. It is awesome, but it is kind of a mess when we just look at it algebraically. So why is it cool? Well, because we have this theorem by Carlsson and Mellit, obviously, that this action actually induces an action of AQT, obviously, on the direct sum of all these Vn's. And it can actually be used to construct a basis for Vn. Namely, if you have d minus to the m and you yi to the y1, yn plus m to the an plus m, d plus n plus m of 1, right, where you take this to be some increasing sequence of integers, then this is actually a basis for Vn. Right, so these operators really are giving you a basis for this space and are giving you a well-defined action of AQT. Great. Okay, so then questions? No? Okay. In addition to this, Carlsson and Mellit also defined another operator. So we have a couple of other operators that we need to introduce into this picture. And they're the following. So we have this operator called omega, which is really just the standard involution. It's sending f to f of minus x and swapping q's and t's. Right, or sorry, inverting q's and t's. And then we have this very special operator called n. It's an antilinear degree preserving automorphism of v. So this is antilinear degree preserving automorphism of v, which is uniquely determined by the fact that it sends 1 to 1 and it intertwines A with A star. Namely, it behaves in the following way, right? So if you conjugate A's, you get A stars and vice versa. So this is going to be this, but then of course, if you do the plus versions or the starred versions, you get the others back. Yi, this is Yi star. N. Okay, cool. So this is the algebraic picture. This is all I want to tell you about it. You have these algebras, they satisfy all these relations. They act on this vector space, which is basically just symmetric functions with a bunch of additional parameters, yi, through these plethistic operators. And then at the end, you have these two additional operators, this n, which, oh, I forgot the most interesting part of it. So n, restricted to v0, actually acts like the nabla operator composed with this omega bar. So here, if you're familiar with Macdonald theory, this is just the well-known Macdonald, or the nabla operator, which diagonalizes the Macdonald eigenbasis. Okay, cool. So this is the algebraic picture. Any questions before we have 3 more minutes before I start on the topological picture.
When you say it's a basis for Vn, do you mean it's a basis over symmetric functions?
Well, you get q's and t's here, so you can actually generate, you can generate the e's using this, I think. There's an explicit formula for it.
So it's just a basis as a vector space?
I think so.
Over Q, yeah.
I think so, over QQT, yeah. Yeah, if I have time, which based on how quickly I'm writing, probably not. You can actually, I'll give you some examples of some symmetric functions you can draw and you can just generate using the operators directly. Yeah. Questions? Okay, should I pause now before I start on the topological picture, or should I do 2 minutes of topology and then stop?
Having a pause now makes sense, and we'll just start 2 minutes earlier. Okay. So let's reconvene at 10:28, and any questions in the meantime?
Yeah, I realized this was pretty dry, just because it's a lot of like, here's definitions and pretty boring, but it'll hopefully get more interesting. There's topology coming, I promise, and categorification.
I put a joke in the chat for you, Nicole.
Oh,
I like it.
I don't know where the chat is. Where's the chat? Oh, there it is. Wow, 14 chats. Sorry, I ignored all of them.
You should. There's been banter back.
You should, yeah. Chats are for people who want their questions answered by other people in chat.
That's great.
They'll unmute themselves if they really want to bother you.
Oh, n+2, probably. Sorry, thank you. That's great. Thanks, Matt, for answering all the questions. Exactly.
So this gamma is just like an affine rotation thing, like going around the cylinder?
Sorry, say that again.
Gamma rotates the variables y1 through yn, like
yes,
on a cylinder.
Well,
with the usual q-squared monodromy.
Yeah, and then you have like the yn. You get like the qt inversion or whatever. There's some coefficient that pops out. But aside from that, yeah, it's just rotating.
This gives you an affine Hecke algebra inside, basically, or cylindrical affine Hecke algebra.
For the y's and the t's satisfy an affine Hecke algebra, exactly. Or generate an affine Hecke algebra, yeah.
Oh, that's not what I meant. But I meant the gamma and the t's.
Oh, the gammas and the t's.
So you shouldn't think of gamma as living in an algebraic QT.
It's not there. Okay.
Yeah.
Phi is the rotation in. So phi is this kind of extended rotation inside is extended affine, but it's not invertible.
Okay. Cool.
And y's are not invertible.
If you restrict this representation to Heck algebras, do you get some interesting, what is the decomposition in terms of Young diagrams?
Sorry, say that again. If I restrict what?
If you restrict this representation to the Heck algebra sitting inside it, you're going to get some decomposition into Young diagrams, right?
Presumably. I honestly don't know though. I probably.
But the affine Heck algebra action commutes with multiplication by symmetric functions. So you just symmetric functions times polynomial representation for the affine Heck algebra. There's no interactions. So you just
Okay.
The polynomial representation for the affine Heck.
I see. Thank you.
Maybe to answer Ben's question, so I think you can get whole Littlewood polynomials by taking just monomial and y's and applying d minus a bunch of times. And so this gives you a base as a vector space.
Oh yeah, this presentation, is it sort of like nicely amenable to Bergman-Diamond lemma?
I don't know. I mean, we chose it just because when we were thinking about like actually categorifying it, which was the goal, it worked nicely, but I don't know. Matt, do you know the answer actually? Maybe Matt wondered off.
Can we repeat?
I was just asking whether this presentation of AQT leads to an obvious PVW basis of it, whether you have the Bergman-Diamond lemma proof. That's how you know you have the right presentation, frankly.
That's why we needed this presentation. It's sort of computable. When you multiply by generators, you know how to expand again into generators.
Right. When you proved that, but so you have an obvious basis then, where things are in order, basically.
Yeah.
Sorry, did the question get answered? My internet cut out.
Yeah, that's all good. And now it's time to resume.
Okay. Sweet. Okay, so now we get to the fun part, which is drawing pictures. Wonderful. So now we move on. So what is the topological picture, which is what I wanted to get to? Right. So in order to do this, let's just very briefly recall some things. So we're going to obviously think of the Heck algebra as just assigning positive crossings to Ti and negative crossings to Ti inverse. Right. So this is hopefully very standard to everyone, right? Where the relations then become basically just the Skein relation, the Heck algebra relations become just the Skein relation and the braid relations. And then in addition, so what that allows us to say is that we can basically just see Hn as the span over Q of basically just braid diagrams, right? Where these are braids up to Skein relations or mod Skein relations. Right, so this is pretty standard. Moreover, we can also do the following, which is what if we take a quotient, right, and just quotient the left and the right action, then that allows us to view this quotient just as the closure of this diagram, right? Where again, we're taking braids, mod Skein relations, or mod the Skein relation, right? And in fact, this is exactly, if you remember the work of Morton and Aston, this is exactly how you would show that there's an isomorphism between the following things, which Hn quotiented by Hn, right? That this is actually secretly nothing more than just basically what we're calling Q0, right? Which is QQ with no Ys. So, right, and here the isomorphism is really just the fact that you're sending the elementary symmetric function to a multiple of the closure of this braid, where if this is K, then these are K strands. And likewise, the homogeneous symmetric functions would then correspond to exactly the same thing, a multiple of this, but with the crossings inverted, right? And then of course, in this paradigm, then you have Schur functions correspond to closures of Young idempotents. Right? So these are Young idempotents. Okay, cool. So the question really is, how do we incorporate the Ys into this picture, right? So the question is how to incorporate the Ys. So in order to do that, we point out that we can show that if you take Hn plus m, and instead of identifying all of the action, but just part of it, right? We just identify the left and right action of Hm, m plus n, then this is actually just the span of taking the diagram, and instead of closing all of the strands, you just close the rightmost m of them, right? So here, this is m, and this is n, right? And here the same thing holds, so this is still a braid, and this is mod skein, and then I guess ambient isotopy. Right, cool. And then what that allows us to say, basically immediately, is that Vn, we can just view it as the direct sum of the span over m bigger than or equal to 0 of this exact same thing, right? Except that rather than just taking these pictures, we have an additional condition, which is that D is, of course, just a braid, but in addition to just being a braid, we also want the condition that it absorbs symmetrizers from the bottom, which is to say that if you tensor with Pn on the bottom, here on the first n strands, where Pn is this Young symmetrizer, you just get D back, right? And then obviously mod skein and ambient isotopy. So, right, this condition again is just telling you that if you take D, right, and then you have these pieces here that you're supposed to be closing off, right, these are identified around the annulus, then if you put a Pn here, this is just, you're just gonna get D back. That's what this added condition is. Okay,
Good question.
so, yes?
In the m, so like we have like y1 through yn. So do I think of m as somehow being like a degree of things in y's?
So the m are the symmetric polynomial side, I guess. It's what the degree of the symmetric polynomial that's living in here is. The n's, these are the y's.
Ah, okay, I got my
Yi ranges from 1 to n. Ti, the Hecke algebra operators, range from 1 to n. And the m is really just has to do with symmetric functions.
Okay, great, thanks. I was getting n's and m's mixed up, thanks.
Yeah, sorry.
And x's and y's mixed up.
Yeah, the x's are symmetric functions. The y's are really the ones we care about.
Sorry, can I add?
Yeah, of course, Matt.
Multiplication by y does in the end increase m, though.
Yes, okay. But I guess what I'm saying is
It'll be clear, I think, from what you say next, like what y's and everything correspond to.
Yeah. I guess all I was saying is that yi's have to do with the n, not with the m number directly. Like that's all. But anyway, it doesn't matter. Let me draw the pictures and then it'll make sense, hopefully. Okay, so then what is the actual action? So let me just keep this here, right? Vn, so we want to define an action of these operators on this vector space. So then the AQT action is given in the following way. So if we're going to say let D be, let's say Vnm, and I'm specifying n and m so that we're clear that D has n strands here, and then it has m strands identified, right? So here, this is glued, this is m, and this is n. Then we have the following. So then Ti is going to act on D in the following way. So it takes D, right? And remember that T's are supposed to be the Heck algebra operators. So as expected, they take the ith strand and swap it with twist it with the I plus first strand, right? And then they leave everything exactly the same. So this is still M, right? So that's the action of Ti. All right, that's great. What other actions do we have? Well, we have the action of D minus. So what D minus does is it takes these diagrams, right? And it takes, if this was 1 through n, right? It takes the nth strand and it moves it over. And it basically closes it around the annulus. So now you just have n minus 1 strands, and it does the same thing here. It takes the nth strand and it closes it up. So that's D minus, right? So what is D minus doing? D minus is going from what? It's going from Vnm to Vn minus 1, m plus 1, right? Because this increased by 1. Okay, what else? Then we have the action of D plus of D. What is D plus going to do? So it's going to take your diagram again, and it's going to multiply on the bottom by Qn plus 1. I'll tell you what that is in a second. Well, it's going to add a strand and then multiply on the bottom by Qn plus 1. So Qn plus 1 here, this is nothing more than just a multiple of our Young symmetrizers, right? So in particular, Qn is something like minus Q, or I guess the minus here doesn't matter. It's Q to the minus 2n minus 1 times Q squared Pn, where Pn is just your Young symmetrizer. So it's just a scaled multiple of Pn. All right, so that's what D minus does. It adds a strand and multiplies on the bottom. Then we have the action of phi of D. So phi is going to take your D, and it's going to, first of all, take again the nth strand here and wrap it around the annulus, right? I want you to remember that these are all wrapped around here. So it comes back and then it goes under all of these and then it goes back up. So that here you have 1 through n because you took the nth strand and you moved it over. So you have n strands on the bottom, and here you have 1 through n, but here now you have m plus 1. Okay, and then lastly, we have the action of yi, which is going to do something really similar, right? In the sense that it takes the ith strand now, it goes under all the strands to its right, it merges with the m's over here, so this becomes m plus 1. It goes under all the strands on the bottom, and then it goes over all the strands before it. And this is the ith strand. And this is yi. Right, so you have these, actually, let me call this is really not AQT action yet. This is the A action. This is the A action. So you have this algebra that was previously defined as these plethistic operators, but then when we change paradigms and we just work with our vector space being this, semi-closed annulus, then our operators suddenly become a lot simpler. And then of course it's a theorem, as you would hopefully expect given the title of the talk, due to Matt and myself, that these topological operators induce an action of A on Vn. In particular, they satisfy the million relations that I wrote last time for A. All right, and the proof is just really topological. There's not much else to it. So I want to point out that here in this topological setting, you'll notice that there are no t's, right? And the reason is that I'm actually setting t equal to -1 in what happened here. So if you look at the original paper by Carlsson and Mellit, the q's and the t's there do not correspond to the q's and the t's that I am using in this normalization. So in their normalization, q equals t inverse, which is why, or t equals q inverse, which is what I actually have in the abstract. But for us here, given what I've written on the slides here, then you just want to set t equal to -1 in the algebraic picture, and then you get this topological picture. So, okay, great. So then, of course, you want A star, right? You don't just want A. So then, well, clearly, we can analogously define A star. So then we have the A star algebra. And what is that one? So the action of that one on Vn is going to be given by the following. So here, the star operators come shifted by this q squared, whatever. And it's the same idea where you start with D, and then for D star, you again multiply, you add a strand, you multiply by another multiple of Pn of your Young symmetrizer. In this case, we're going to call it Q prime just because it's a different multiple. And then what this does is not only does it add a strand, it also takes your strand and then it wraps it around everything. So it comes back and it does this little thing, right? So this, remember, this was previously what was gamma composed with some plethism, the gamma that Ben was asking about, and now it just became this, right? And again, here, these strands are identified with these strands, right? And just, if you're curious, this Qn prime is really just minus q to the 2n minus 4 Qn. So it's just another multiple of Pn. And then in addition to D plus, of course, we have phi star of D, which is minus q squared. Like I said, all these start operators come with this coefficient, right? And what this one does is it takes your last strand, so in this case, your nth strand, and it passes it past your m strands, it closes it around the annulus, and then it comes back here, and then it goes under everything, and then back here. So if here you had 1 through n, here you still have 1 through n, but now you have n plus 1, right? And then likewise, you can define yi star of D to be the following. So this is minus q squared. How am I doing on time? Ooh. Okay, I should hurry up. D. And then here you take your ith strand, you cross everything with your ith strand, right? You bring it, you close it around the annulus, and then again, you do the same thing. You come back, go under everything, you go under this one, and then you go back to the ith spot. So here you have 1 through n, you still have 1 through n, and then you have m plus 1. These are identified. Okay, and then of course, no surprise, theorem again, right? That this induces an action of A star on Vn, of course, and then consequently, actually, moreover, maybe not consequently, moreover, we actually also get an action of a qt on Vn. And again, this is specialized at q equals t inverse, right, at this point, consistently for the topological part. Not just Vn, the direct sum of Vn's, right? And then this part of the theorem, well, this is just proving that the start operators satisfy the slew of relations for the A star algebra, and then proving that you actually get a well-defined action of AQT is just, again, proving that you satisfy these mixed relations between the two, right? Okay, any questions? Otherwise, I'm gonna continue with one more operator, what n is. All right, nothing, great. I'm either really clear or everybody's asleep and nobody cares, so.
Everybody's
whatever.
happy.
All right, so this is great. This gives us a really nice, well-defined action of this algebra that was previously kind of messy and a little scary to look at. So then lastly, I also wanted to tell you about what this n operator is, right? Remember that this n operator was what was, I told you that it intertwines the action of A and A star, right? And it sends 1 to 1, and then it acts like the conjugate or the composition of this involution with the nabla operator on V0. So topologically, we can see this operator in the following way. So n of D, right? We're going to take it. So it's got some normalization, whatever, doesn't really matter. But the point is, what it does is it takes your braid, your diagram D, it composes it with a full twist on top. Actually, let me say this. So the first thing it does is it takes your diagram D, and D bar is just D with positive crossings and negative crossings swapped. So Ti becomes Ti inverse and vice versa. And then Q and T get swapped for Q inverse and T inverse, right? So you do that to your diagram. You don't flip it upside down, just swap negative and positive crossings, and then you swap Q's and T's, or invert Q's and T's. And then you compose it on top with a full twist on n plus m strands. And that's n. And then, of course, it's a proposition, theorem, whatever, fact.
Question, your original D starts with n plus m strands or just n strands, then you're putting extra m on later?
Oh, no. My original D is this one. So it starts with n
It
plus
does have n plus m. Okay.
Yep.
Yep. Nice.
And so it's a fact precisely that this n actually intertwines. This topological n, so maybe I should write n top, intertwines. I don't know how to spell intertwines. Intertwines the A and A star action, as you would expect, right? It conjugates one and gives you the other. Sweet, awesome. Ben, how much time do I have left?
Until like another 7 minutes.
Okay, wonderful. That's great. Then I'm totally going to skip the symmetric function story. Does not matter. Okay, so that's the end for the topological part, which is really just defining these topological operators and then saying, hey, look, it's all well defined and it gives you exactly what you want. I'm going to move on to the categorical component. Any questions before I move to the last part of this? Nope. Okay. Great. In that case, let me proceed. Sorry, this I don't have written by hand. I had it written on a slide. Here we go. Okay, so in order to compute the categorical action, so the categorical part, categorical action, we need a couple of ingredients. So first of all, Q now is going to denote Zergo bimodule grading. We have T is going to be some homological grading. And then we need some ingredients. So what are my ingredients? So the first ingredient I need are these categorified symmetrizers that I'm just going to cite all of Matt's work for this one, Hogancamp. And namely, they're basically just chain complexes defined in the following way. So we can do bi1, bi2, censored with bi3 to q squared, bi1, bi2 to QBI, right? Where BIs are these Bott-Samuelson bimodules. And then you have the identity, which lives in homological degree 0. And these projectors, right, these categorical symmetrizers satisfy some really nice relations. In particular, they kill or are killed by Bott-Samuelsons, which is awesome. In addition, they also have a family, so PN, they have a family of some really interesting endomorphisms. Endomorphisms, which we're going to call UI, where I ranges from 1 to n. And these are interesting in the sense that they actually generate the cohomology ring of the endomorphism of Pn. And then associated to these categorified symmetrizers, we have some other chain complexes. We're going to call them QNs, right? And these are basically just defined as the cones of these UNs, right? So they're TQ inverse 2 to the minus 2n of the cone of UN, right? Which, if you want a more explicit construction, is just the cone of TQ, T inverse squared, Pn to minus 2n Pn. Anyway, the point is they're the cone of this endomorphism, the UN endomorphism. Okay, so once we have these pieces in mind, how do we actually construct a categorical Vn? In order to do that, we're actually going to build upon recent work of Gorski and Matt and Paul Wedrick, right? So categorical Vn. And so the main ingredient here is, again, this Gorski, Hogancamp, Wedrick construction recently that's found in their paper on derived traces for circle bimodules. Right, and the main idea, I'm not going to do it. I'm not going to do it service at all. I apologize in advance, but this is, I think, Paul took two talks completely to explain in our seminar, so I'm not even going to try. But morally, it's basically a category whose objects are going to be Bott-Samuelsons, Bott-Samuelson in SBIM M plus N, right? And you want to think of these as living on this cylinder, right? So that its morphisms then are going to be basically Elias-Williamson diagrams, where I'm going to just say something that's totally vague, and I apologize for that. Near the seam, and I'll explain what this means in a second, is in SBIM M. So the way these diagrams are constructed is you have certain, let's say, seams along your cylinder, and then if you, let's say you have X and X prime, these are some sequences of Bott-Samuelsons, then you're allowed to put little morphisms here, but some of the morphisms can wrap around the cylinder, right, all the way back. And the point is that the things that cross these purple lines, the things that cross the seams, have to be in SBIM N. And then what this is basically telling you is that using their construction, you can actually get an explicit DG model for SBIM M plus N with the left and right action SBIM M action identified. Right, and then in this world, basically the differential is just the usual bar complex, or sorry, the usual bar differential, where it's just taken by taking alternating sums of deleting these purple walls, right? And then everything is taken up to, I guess, isotopy, or preserving the purple wall, preserving isotopy. There we go. Anyway, so you have this construction, and what we're interested in is not precisely their category, but a modification of it. So we're going to let C prime be the pre-triangulated whole, related whole of C, right? This category up here, which some of you might be happier if I call it finite one-sided twisted complexes. And then we're going to let Vnm, which is our categorical version of Vnm, be nothing more than the full subcategory of C prime, right, with complexes that satisfy the following properties. First property is that they kill BIs from below. So namely, if you take one of these chain complexes and you tensor them with BI, you get your homotopy equivalent to 0. And on these chain complexes, you need, or you want, the UIs, right? So U1 through UN to act null homotopically. Right. So the fact that you kill BIs is basically just telling you that you're absorbing projectors from the bottom. And then the fact that these UIs act null homotopically, well, that's related to something else, but the UIs are really just these interesting endomorphisms of U. Okay, cool. So what do we actually want then? Now that we have these VNMs, right, which is just this full subcategory of C prime, we can actually directly from here, we can basically just directly lift the action of AQT to this categorical VNM, right, by just reading the diagrams where every crossing then becomes a Rukia complex, and then you just lift everything correspondingly, right? So, for example, right, TI then becomes the functor from VNM to VNM that's taking your chain complex and then just tensoring it with TI, where TI is, of course, the Rukia complex for TI, right? Which, just for consistency, it's this one. All right, okay. What else do we have? Well, we have D minus, right? What is D minus? So D minus is the functor from VNM to Vn minus 1, m plus 1. And what is it? It's the identity on objects, and it's the inclusion on morphism spaces. Right? What about D plus? D plus is then a functor from VNM to Vn plus 1 m. And what does it do? It takes a chain complex. And then again, this is the part where you literally are just reading the diagrams that we had below, previously the topological diagrams. Right? And what are you doing? You're first multiplying on the bottom by this chain complex Qn. And I'm going to write square. I want to differentiate between taking vertical, so this is vertical tensor product, so vertical composition or versus horizontal concatenation. So this is horizontal, right? And then there's a way of actually formally defining these so that it all makes sense in chain complex land. But for right now, let me just say this, right? And then literally this is just reading the topological pictures that we had before, and then etc. I'm not going to go through and parse
You're a couple minutes over time, so try to.
Sorry, this is literally, I'm at the end.
Okay.
I mean, and the main point is that it all works. It all works, and you get all the Carlsson-Mellit relations that lift over to basically relations up to homotopy. Right. And the only one that's semi-interesting in the sense that it's not literally this is homotopy equivalent to this is the relation that phi is basically TQ inverse to whatever 1 minus n or something. This commutator, the fact that this actually lifts to just a cone. So this becomes the cone of the following map D plus D minus to TQ inverse and B2. Right. But everything else is literally just a direct lift. And that's it. That's all I wanted to say. Thank you.
Thank you. All right. Are there questions to the speaker?
I think all the questions got asked in the chat.
I added a new one to the chat, but if other people have more exciting questions, I'm fine for them to leap in. So my question's about you. When you were, before you got to the categorified picture, you talked about, okay, this is happening, this acting on the space is really at t equals -1, or you said something about, q and q inverse. But here you were like, well, t and q are these, homological or circle bimodule degrees. And so what's happening with saying you had those specializations before? Does that mean you actually don't need to?
It's like a partial decategorification, if you want to think of it that way. Hello?
Is it just that t is -1 when you take the Grothendieck degree?
T is just -1, yeah. It's just specializing it, that's all.
But does this, you don't, it looks like you can say what's happening even if you don't specialize, that you can just, or I'm confused.
I think t is just now the homological shift, Monica.
T is just a homological shift, yeah.
Yeah, okay.
So this, I would say that this is a recurring point of confusion, and rightfully so, that here in the original Carlsson-Mellit picture, we have something that appears to be decategorified because it's just vector spaces and linear operators, and yet it still has q's and t's. So what we don't know how to do is describe that whole thing topologically. Like there's this kind of intermediate step.
You need a DG lift or something.
Sorry?
Like you need things to be true in chain complex land without the homotopy or something.
No, you need an extra grading on everything.
Oh.
So you need to be able to distill out some of the t's from the -1s. And for this, you need some additional grading on the categorified side. Anyway, we don't know how to do that extra grading, but if we did, we get t. We'd have a decategorification that still remembered something about t. Sorry to, but
No,
yeah,
no.
Monica, you're right to be confused because it's very confusing.
Thank you.
So this cone at the end,
Yeah.
is like it's like saying what happens when you, maybe I have it backwards. You take like qn and then you forget one of the variables.
So, okay, yeah, so this cone, okay. So remember how I told you that there was these q's?
Mm-hmm.
There's relations involving the q's, and this cone just is literally just a consequence of the relation between, some recursion relations between q's and p's.
Okay.
It's technical mumbo jumbo, yeah.
However, this is technical mumbo jumbo I like.
I know. But yeah, it literally just comes out of the fact that the recursion relations between qn+1 and pn. And in order to have the relation hold, it becomes this, naturally, because q itself is a cone of these p's. And when you're taking this commutation relation, you're basically taking like pn+1 and decomposing it as like the sum of two smaller symmetrizers.
Right.
And so then this is where the cone, yeah, anyway, that's it.
I think there are more relations. So in AQT, sometimes you have relations which have 3 terms. And then you want to ask, do all these relations, can all of them be explained by a triangle in the category?
Which relation, sorry?
I mean,
like phi composed with t composed with y or something like.
No, like some very specific like relations with 3 terms. Like for instance, in the computation of the homology of torus nodes.
Mm-hmm.
Every step you use some relation with 3 terms, and this corresponds to a complex, to a triangle.
Uh-huh.
So this is somehow still doesn't follow from.
I don't think we've looked at that specifically.
Not clear from this picture why.
I think it's the same recursion though, no? It's like the same recursion for symmetrizers eventually.
No, it's a little different. So, sorry.
Matt,
I think I'm sorry to butt in here, but I think it seems like Anton is asking about this sort of recursion that relates like the symmetrizers and like a strand wrapping around the symmetrizer with a larger symmetrizer. You know, this kind of through-term relation.
okay.
And that's sort of different in flavor from this commutator relation between D plus and D minus.
Right. Yeah. Exactly.
And yeah, I don't
think we looked at that at all.
Well,
Or maybe you did, but we didn't.
it's just not something, yeah, the relation that seems to be like useful for computing knot invariance doesn't seem to be like, it doesn't seem to have a nice expression in this language, as far as I know. So like, yeah, this commutator relation between D plus and D minus is like, you could imagine taking a projector sandwich. So you have Pn minus 1 and Pn minus 1 with a crossing in between them. There's a linear relation relating that guy and the larger projector in Pn minus 1. And this is that relation in disguise.
The Jones-Wenzel recursion.
Well, the Jones-Wenzel recursion where the thing in the middle is not the Bott-Samuelson, it's the Rigier.
Yeah.
It is some other relation which you didn't list, but you can get it as a combination of other relations in the AQT algebra. And then the statement would be that, well, that in the categorification, that relation also holds.
Which relation, Anton? Do you know, like, which one are you talking about?
I mean, maybe.
We would love to know more about what.
Let's figure this part out later. Are there any other questions?
So this subcategory that you're taking, so can I think about it as you take like this C prime and then you heat it with projector or like compact projector on below?
Yeah, so this condition here, the fact that it killed Bott-Samuelson's is equivalent to the fact that it has basically, you can think of it as it has a projector on the bottom living on it, or it absorbs projectors on the bottom, however you want to interpret that.
But basically I can always like just take all diagrams and put projector on the bottom and then like draw this with this extra projector on the bottom. Something like this.
That you're saying you can always put it there, or I guess?
That's the question. So, I mean, so I have a diagram with like, with no condition, with just anything in C prime, basically.
Yeah.
And then I add this projector on the bottom.
Yeah.
And I look at this subcategory. Is it the same?
It should be. I mean, modulo like U1 through UN acting null homotopically, right? Assuming you have that condition, then yeah.
Are you assuming like complexes are bounded or anything, or?
No, so actually, okay, that's a technical point that I pointedly avoided. So sometimes everything is finite up to homotopy. But sometimes they're not actually finite, but they're all finite up to homotopy.
Mm-hmm. But I guess you can put this projector and like cone of all these UIs acting on this projector. So you just put this whole thing there. And then they would act non-homotopically. Whatever, we can talk later.
Yeah.
And another question, like, can you draw the proof of Shuffle theorem with all this diagram?
No, not yet. We want to, but not yet. And part of that comes from the fact that we're trying to understand what the symmetric functions are. So we have pictures for like, you know, the dig path symmetric functions. We have pictures for all the symmetric functions, but how it all fits together is not 100% clear yet.
Mm-hmm. And can you draw this computation of torus knot homology like that Ben and Matt and Anton did?
I think that's the same question we've just been discussing with the triangle. All right, these are good questions. Let's thank the speaker again.
Thank you.